So today we are moving with chapter 3 data representation. In this chapter, we are going to learn the representation of data and information, number systems, conversions, basic operations. About all these things we are going to study one by one. The first one is introduction. In digital computers, data and the instructions are stored in computer's memory using binary code, or we also call it as machine code, which is represented by two digits, that is 0 and 1, which are called as binary digits. Stands for bit, BIT. B for binary, IT is taken from digit, so it is bits. So the data may contain digits, alphabets, symbols, right? Later on, once you enter it, it will be converted to binary digits. So once, and all the arithmetic operations and all the processing work, it will be done in the by using binary digits itself. So it is very important to understand different number systems uh, is necessary. Different number systems which are present in the computer for data representation. The number system uses well-defined symbols called digits. The values of digits depends on the position in which they appear in the number. So there are basically two types of number system: non-positional number system and positional number system. Where in the non-positional number system, in the early days, the olden days, people used to use this kind of number system for doing simple calculations like addition and subtraction. Where in this non-positional number system, they used to have some symbols for representing the numbers. They were not having direct numbers like what we are using nowadays. The one example for this is Roman number system, where this is an example of non-positional number system, where you can see that when we write I, so it represents 1, V represents 5, X represents 10, L represents 50. Like this, by using these kind of symbols, they used to represent the numbers. Each and every symbol, they represent some value irrespective of the position. Irrespective of the position, right? This number system cannot be used for complex calculations or arithmetic operations, right? That is why one more type of number system got improved. That is what positional number system. In this, we have decimal, binary, octal, and hexadecimal number systems, which are positional number systems, right? So in all these number system, the one special term is what we will be using: base or radix of a number system. That means it represents the total number of digits which are present in these number system, right? That is called as what? Base or a radix of a number system. Every number is represented by base. Every number is represented by base, right? That means in this, for example, base or a radix, both are same. For example, a number base is a x, right, which represents x digits. See, for example, here I'm writing a number, say 5. Then after that, I write 10. Wait. So now here I'll take this. See, this means what? 5 is a decimal number. 5 is a digit taken from the decimal number system. Pi is a value. The 10 indicates base or a radix, right? For every number system, there is a particular base or a radix. Base or radix in the sense what? How many, the number of digits present in that number system is indicated by that base or a radix, right? So now here, the base or a radix of a number system is the total number of digits present in any number system. Now, first one is decimal number system. This is the most commonly used number system in our daily life, right? In every routine life, whatever the number system we are using is, majority is, it is decimal number system only. It has 10 numbers ranging from 0 to 9. Hence, the radix or the base of a decimal number system is 10. So, the positional values are expressed in powers of 10. In powers of 10. So, now for example, here you see there is a value 542.76 base 10. That means it's a decimal number, which can be represented in equivalent value as 5. See, all the digits, first what do you do? From right side up to left side, everything you write like this. See, 5 into 10 plus 4 into 10 plus 2 into 10 plus 7 into 10 plus 6 into 10. So before the decimal point, what we have for that base 10, you give the powers from 0 towards left in the increasing order. So in the integer part, you see here 542 is there, and in the fraction part we have 76. So in the integer part, what this 542 we have, right? 542 we have, in that it is 2 is the unit, 4 is the tens, and 5 is in the hundreds position. Hence, 2 into 10 raised to 0. Before the point, you have to give the powers in positive value. It starts from 0 and towards left, you have to give it in an increasing order, right? 10 raised to 0. 4 into 10 to the power of 1, 5 into 10 to the power of 2. Then here plus, after the decimal point, what we have, for that, what you have to do? From the first digit of the decimal point towards the right, you have to give the powers from -1 because 0 is already given. So 7 into 10 to the power of -1 plus 6 into 10 to the power of -2 and so on. So here, the following table will show you the weightage of the positional values of the decimal number. So here you see in the columns we have hundreds, tens, units, 1/10, 100, and in the rows we have weights, digits, and values. So the digit 5, it is in the hundreds position, so it is 10 raised to 2. 4, it is in the tens, so 10 raised to 1, as it is in the second place. And 2, it is in the units part, so 10 raised to 0. And 7, it is after the decimal point and the first digit, so 10 raised to -1. 6 is the second digit after the decimal point, so it is 10 raised to -2. So 5 into 10 raised to 2 gives you 500. 4 into 10 raised to 1 gives you 40. 2 into 10 raised to 0 gives you 2. 7 into 10 raised to -1 is 0.7. 6 into 10 raised to -2 gives you 0.06. If you sum all these values, 500 plus 40 plus 2 plus 0.7 plus 0.06, you will get the original number 542.76, right? This is how decimal number system moves. First, we are going to study all the number system. Later on, we are going to study how to do conversion from one type of number system to another type of number system. Now, the next one is binary number system. Binary So this is like very popular one in the computer field, right? Who are having more touch with the computer, this binary number system is quite common for them. So as the computer understands only binary language, where it has two digits, 0 and 1. Even it doesn't understand these digits also, it understands or it represents these digits in the form of voltage. 0 stands for low voltage, 1 stands for high voltage, which is suitable to represent bistable of electronic components. The representation of data in a computer is usually in binary digits 0 and 1. Hence, the base is 2. There are only two digits. The total number of digits present in a binary number system is 2. They are 0 and 1. So, whenever you are writing the binary number, remember you have to write like this. Say I am writing 10111 something, then in the bracket, it should be like this, right? So then only it's a binary number. And if you are not writing anything in the bracket, by default it is considered as a decimal number system. Then they'll read it as a 10,111. But if you want to say that it's a binary number, always the base or a radix, you must write it in the subscript part as a 2 in bracket, right? To represent. So we will read it as 10111. So here, how this numbers in the binary number system will be represented, that part we will see now. The representation of data in a computer is usually in binary digits 0 and 1, hence the base is 2. The positional values are expressed in powers of 2. See, the positional values are expressed in powers of 2. It is very essential to know how to count a binary number and also the conversion from binary to all other number system. This is very important, right? So here, so let us see, there is a number here. Once again, if there are like decimal values, you have to take it in the negative side, right? Negative powers. So first we will see simple one. See, this 1011 is there. How it will be represented? 1 into, see, 1 into 2 plus 0 into 2 plus 1 into 2 plus, and then again 1 into 2 plus 1 into 2, right? So this number is not having any decimals. So 0 power, and then here raised to 1, and this is raised to 2, and this is raised to 3, then this is raised to 4, right? So like this, the digits representation will be there. If there are any decimals, then again you have to continue in the powers values, you must give it in the negative. 10 raised to minus 1, sorry, 2 raised to minus 1, 2 raised to minus 2, or towards right, okay? So now here you can see the same table, what we saw in the decimal number system. We have weights, bits, and values. So here, the total number, what they have given is 11011, right? Then 101 is there. These are in decimals. Okay. So you can see here, before the decimal point, 11011 is there. So 2 raised to 0, 2 raised to 1, 0 into 2 raised to 2, 1 into 2 raised to 3, 1 into 2 raised to 4. After the decimal point, what we have? So it is 1 raised to 2, 1 into 2 raised to minus 1, 0 into 2 raised to minus 2, 1 into 2 raised to minus 3. Then you calculate the answer. 1 into 2 raised to 4 is 16, 1 into 2 raised to 3 is 18, 0 into 2 raised to 2 is 4, and 1 into 2 raised to 1 is 2, 1 into 2 raised to 0 is 1, and then similarly the negative values are calculated, right? So like this, the numbers will be represented. In the binary system, 11010 base 2, right? The leftmost bit 1, see the leftmost bit 1, right, is the highest order bit. It is the highest order bit. We call this as what? MSB, most significant bit. This may comes in MCQ question. A rightmost bit is how much? 0, where this digit, it is the lower order bit, so it is called as least significant bit, LSB. Right. Next we have octal number system. Octal number system. So now whenever you are studying the number system, what you should see first, what is the base or a radix in this? The radix or the base of the octal number system is 7. So it represents the digits from 0 to, radix is 8, but the number of digits what it will represent, so it ranges from 0 to 7. Octal numbers base or a radix is 8, not 7. And the digits what it represents is 0 to 7. The positional values are expressed in powers of 8. In the decimal, we saw that the positional values are expressed in powers of 10. In binary number system, we saw that the positional values are expressed in powers of 2. In the same way, the positional values are expressed in octal number system is 8. So there is a value 234.56. So here in the same way, see 234 is there before the decimal point. 4 into 8 raised to 0 plus next digit is 3. 3 into 8. First, what do you do? Every digit multiplied by 8 you write, including all the decimal. Before the decimal point, what we have towards left, no? Just give the powers in a positive value starting from 0 in the increasing order. 0, 8 raised to 1, 8 raised to 2. And from the decimal point towards right, what we have, give the powers 8 raised to minus 1, 8 raised to minus 2, right? And this table you see, it is same as those above number systems. So if 2 raised to 2 into 8 raised to 2, 3 into 8 raised to 1, 4 into 8 raised to 0, 5 into 8 raised to minus 1, 6 into 8 raised to minus 2. So all these values, after manipulating all these values, we get these values. If you sum these values, so you will come to know the final value 234.56, right? So now here, hexadecimal number system, right? Okay, hexadecimal number system. So in this, the total number of the number system has 16 digits. That means what? The base or a radix of this number system is 16. But this number system is a little special compared to any other numbering systems, because in this 16 digits are represented in a special way. That is 0 to, in the range 0 to the 16 digit, all are not numbers. 0 to 9 are numbers. That means what? The first in 16, the first 10 are what? Numbers only. 0 to 9. From 10 to 15, 10, 11, 12, 13, 14, 15, 6 digits are represented by alphabetical letters. A, B, C, D, E, F. Right. That means A letter represents 10. See, 0 to 9 are numbers. 10 is represented by alphabetical letter A. 11 is represented by alphabetical letter B. 12 is represented by C, and so on up to F. The F represents last number 15. So here you see the hexadecimal number system, how it looks like. 5A and 5AF. See the number 5AF. Point D is there. See, point D, alphabetical letters are there. There is a decimal point in that. But alphabetical letters are what? They are representing the numbers, right? So here first what you have to do, as the base or a radix of a number system is 16. So 5 into 16 plus A into 16 plus F into 16 plus D into 16. First write like this. Before the decimal point, the first letter is F, right? So 16 raised to 0 for F, right? Then next letter is A is there. So A is in the tens position. So A into 16 raised to 1 and 5 into 16 raised to 2. And after the decimal point, as usual, D into 16 raised to minus 1. So 16 raised to 2 into 5, 16 raised to 1. A is there. A stands for how much? 10. 16 raised to 0 into F. F means how much? 15. Right. So it should be done like this. Okay, anyhow, down examples are there. There we will verify, or you can see once. See what they have done. They have written 5AF, point D, and then 16. 16 is the base. So it should be written like this. Let us calculate the value for this. 5 into 16. See how you have to calculate. A into 16, then plus F into 16 plus D into 16. This is raised to 0 and this is raised to 1. In computer showing this process will be little late, no problem, but we will do raised to 3. But this one minute, D actually minus 1. It is little wrong. This is in decimal, no. This is minus 1. And this is 0. And this is 1. And this is 2. Okay. This is the result. So now you have to calculate the answer for 5 into 10 to the power of 16. Let us use calculate. So 16 into 16, 16 raised to 2, no? 256 into 5 is how much? 261. That we will write it here. This is the answer for 5 into 16 raised to 2. A means how much? 10. 10 into 16 raised to 1. 16 raised to 1 is 16. Multiplied by 10, 160. Then F into 16 raised to 0. So now F stands for how much? 15. Multiplied by 16 raised to 0. 16 raised to 0 is 1. Multiplied by 15 is 15. Plus. So here it is. So D stands for A means 11, A means 10, B means 11, C means 12, D means 13. 13 into 16 raised to minus 1, right? 13 into 16 raised to minus 1. So 13 multiplied by 16 raised to minus 1 is 0.0625. Answer is 0.8125. Right. So now let us add all this. 160 plus 15 plus 0.8125. The total answer is here. The final answer is this. Right. So like this, hexadecimal number will be manipulated. Right. Okay. So now here, number system conversion. This part is very important. How to convert a value from one number system to another number system. From binary to decimal, decimal to binary, octal to binary, binary to octal, decimal to octal, octal to decimal, like this. From all the way, you should know. And especially what? Numbers with decimal values. Those conversions you must know very perfectly. Then only it will be useful. And in the exams, these kind of conversion questions will be, surely it will be there. Right. So that's why everyone concentrate this part perfectly. And after showing this, so later on, after watching this video completely, later on, what do? You take some extra examples and you try it. Right. So now here the first one is a decimal to binary conversion. Decimal to binary conversion. What is the procedure for this? Divide the given decimal number by 2. See, decimal to binary they have said. That means what? Input value will be decimal number. You have to convert it to binary. That means every digit of a decimal number should be multiplied by 2. Sorry, it should be divisible by 2. Right. So for example, so not every digit, the whole number has to be divided by 2. Divide the given number, given decimal number by 2. Second step, note the quotient and remainder. Third step, repeat the step 1 and step 2 until the quotient becomes 0. The first remainder will be the LSB. See, the first remainder will be the LSB means what? Right, here see, we have studied about that LSB and most significant bit and least significant bit, right? So the first remainder, what you get, LSB means that is the last digit should be there in the binary. Most significant bit means what? It is the first digit should be there in the binary number system. That means the first remainder what you get, it is the last digit, and the last remainder what you get, it is the first digit. That means after dividing that number and after recording all the remainder and quotients, from down to up, you have to write down the digits. That will become the final binary digits. That is what MSB to LSB. There is an example. Here you see. Consider the decimal number 53. Say always you have to observe the base. It's a decimal number because 53 can also be written in octal number. 53 can also be written in hexadecimal number. So always you have to represent. Even after calculating the result, what do you write? No, writing the base is very important, and you have done the calculation, you have done it correctly, but you have not written the base means your answer will be considered as wrong. Right. So here we have 53. So divide this number from 2. See, 2, 26, 26 twos are, it is 53. Sorry, it is how much? 52. So 53, in that 52 will be divided. It will be subtracted. So what happens? The quotient of the division is 26. That you have to write here. Quotient of the division is 26. 26 twos are, right? So it is how much? 52. 53 minus 52 is, it is how much? Remainder is 1. But quotient of the division is 26. Kindly note. That is the LSP. Then continue the division. 2 13 ja. So it is 26. So 26 minus 26 is 0. Then 2 13. 2 6 are 12. 13 minus 12 is 1. 1 is the remainder. 6 is the quotient. 2 3s are 6. 6 minus 6 is 0. Remainder is 0, but quotient is 3. 2 1s are 2. 3 minus 2 is 1. Remainder is 1. Quotient is 1. So here we have 1 is left out. Then after that 0 is there. So what you have to do in this case, here you have to consider in the reverse order, MSB to LSB, right? That is why 1 1 0 1 0 1, right? So, and in the base you see they have written 2, and here you have to write your answer finally like this: 53 base 10 equal to 110101 2, right? So we can try here one example. Excel will try. Say we have 65. Okay, we are dividing it by 2. So now here what happens? 232s are 64, right? Quotient you write here. Remainder is how much? 232s are 64 means 65 minus 64 is remainder is 1. Whenever you divide the number from 2, always you get the remainder only in 0 and 1. That is very important. Then 32 has to be divided by 2. 2 16s are 32. Okay. Remainder is how much? 0. 32 minus 32. Then the next quotient 16 has to be divided by 2. 2 8s are 16. Remainder is 0. Then 2 4s are 8. Remainder is 0. Then 2 2s are 4. Remainder is 0. Then 2 1s are 2. Remainder is 0. Right? So here this 1, then up to this 1. This 1 is what? It is LSB. Sorry, MSB. Most significant digit, bit. And this 1 is what? It is LSB. Right? So when you are writing, always you have to write it in the direction of MSB to LSB. That means 1 down, this digit first. Right? Then this digit, then this, then this, then this, then this one, and last this one. So 1 5 zeros 1. And always writing off this base is very important. So this is Excel, no. So making it subscript is, again I have to go for some settings. Okay, leave it, no problem. So 65's equivalent binary number is 1 for 1 0 0 0 and 5 zeros, no, 5 zeros, 5 0 1, and base 2. 65 is the decimal numbers, equivalent binary number is this. How you have to write? Like this you have to write. In the MS Word I'll show you so that clearly you can see. 65 base 10 equal to 1 followed by 5 zeros 1 base 2. Fine. Like this your answer should be. Okay. So this is how decimal to binary. Right. Decimal to binary. Decimal is the input number and the result what you have to extract is binary number. So that time divide the decimal number from 2 and go on recording the quotient and the remainder. The first quotient what you get, again divide that quotient by 2 and take next quotient and write its remainder. Continue the process, you will get that option. So as I said you, in the exams they won't give you these type of simple questions like say convert 65 to binary, because it's very easy, everyone can do. They always do for fractions, right? Decimal fraction to binary conversion. Learning this process is only important. In such case, what do you have to do? See, decimal fraction to binary it is. Multiply the decimal fraction by 2. Note the carry and the product. Repeat step 1 until the fractional product becomes 0. Okay, this is only about fractional part now, right? The first carry will be the MSB and the last, see, the first carry will be the MSB. This is the reverse of the only a decimal number without decimal part or the fraction part. The first carry will be the MSB and the last carry is the LSB. This is reverse. In the only the decimal number with without fraction part, it uses to be reverse, right? The equivalent binary fraction is then written from MSB to LSB, right to left. See, 0.3125 is there, right? See, 0.3125 decimal number is there. How to convert this one to a binary? In this case, we are not going to make a divide, right? We are going to multiply and we are going to write down the carry. That carry will become binary digits. See, 0.3125 multiplied by 2. So, product is 0.625, right? So, it will be, so 0.3125 multiplied by 2 and you have to record the carry. So, here you see 0.3125 multiplied by 2. 2 5s are 10. 2 5s are 10, right? So what do? We write here 0 and carry is how much? 1. That is written here in the carry part, right? 2 5s are 10, like general multiplication. General multiplication. 0 is written here and carry is 1. After that, 2 2s are 4 plus 1, 5. No carry. After that, 2 1s are 2. Carry is 0. It is 2. 2 3s are 6. No carry. It is 6. Right? Then point. Then 0. 0.625. Like this, we got this 0.625. This product. And here we got 0111. Sorry. So while multiplying this number, at last what carry will be there? No, that you record here. Right, 0. The last carry was 0 and the product was 0.625. Similarly, now we have to continue. This product has to be multiplied by 2. The last carry will be 1 and the product will be 0.25. That 0.25 multiplied by 2, the carry will be 0. The last carry you recorded, it will be 0.50. 0.50 into 2, the last carry will be 1 and the number is, product is 0. That means we need not to continue. So here, therefore, 0.3125 base 10 equivalent to 0. See, you have to take MSB to last LSB. That is 0101. This is taking the binary digit. This is the reverse process for a number without fraction part. With the fraction part, what happens is first carry itself is considered as MSB, last carry is considered as LSB. Whereas in the purely a decimal number, whole number, without fraction number, the last remainder what we get, that remainder is considered as MSB, and the first remainder what we got it is a LSB. That means it is the last digit. This point you have to understand clearly. Now moving to binary to decimal conversion. See, there we did decimal to binary number without fraction. Then decimal to binary where a decimal number with fraction we did. Right. Now we are doing binary to decimal conversion. So where in this multiply each bit, binary digit will be the input value, and the output what you have to produce? Decimal value. Right. So multiply each bit of the binary number by its positional weight. By its positional weight is what? Binary's positional weight is 2. Add all the products, right? You will get the final answer. The given number is 11011.101 and base is 2. This is the binary number with a decimal they have. This kind of numbers only you have to practice. So first what do? You have to write 1 multiplied by everything. Like here I'll show you one. Here we wrote 11011. This is the number, right? 0.101. This is the number what they have given. Fine. So what do you have to do now? First 1 multiplied by 2 plus 1 multiplied by 2 plus 0 multiplied by 2 plus 1 multiplied by 2 plus again 1 multiplied by 2 plus now decimal values 1 multiplied by 2 plus 0 multiplied by 2 plus 1 multiplied by 2. Now give the powers. See, from here these are decimal part. From here it is integer part. So I have to write here raised to 0 and then here raised to 1 and this is a raised to 2 and this is a raised to 3 and this is raised to 4. And now here what do you have to do? This one minus 1 minus 1 minus 2 and minus 3. Right. So what do you have to do? You have to calculate the product like how I did know here. In the same way 1 into 10 2 raised to 4. Right. So here so 1 into 2 raised to 4 is how much? 2 raised to 4 is 16. 16 ones are 16. Then plus 1 into 2 raised to 3. 2 raised to 3 is 2 into 2 into 2. 2 into 2, 4. 4 into 2, 8. 8 ones are 8. So 0 into 2 raised to 2. It is 0 only. Plus 1 raised to 1 into 2 raised to 1. 2 raised to 1 is 2. 2 into 1 is 2. 2 raised to 0 is 1. So 1 into 1 is 1. 1 into 2 raised to minus 1. So 1 into 2 raised to minus 1 is 0.5. Multiplied by 1 is 0.5. Right. Plus 0 only. Plus 1 into 2 raised to minus 3. So here in Excel I am calculating 2 comma minus 3. It will be 0.125. 0.125. Now add all these values. So you will get the final result. So 16 plus 8 plus 0 plus 2 plus 16 plus 8 plus 0 plus 2 plus 1 plus 0.5 plus 0.125. So it is 27.625. This is a decimal number. This is at last you have to write the answer like this. Equal to, you can say here, therefore, like this you have to write. The base should be come down like this. Fine. This is the way of converting binary to decimal. With fraction number only they have shown. Next. So here also with the table only I have given here 27.625. Decimal to octal conversion. Next one. One moment.